It began quietly, a flicker on a control room screen, unnoticed by busy technicians juggling coffees and phone calls. Outside, planes roared into Heathrow Airport, passengers rushing to gates, unaware of any danger. Nobody realized yet that this small, fleeting anomaly hinted at something deeper, a subtle fracture in the digital foundations of London's power system. Hours later, Heathrow was paralyzed, flights cancelled, terminals darkened, tens of thousands stranded. At first glance, the cause seemed obvious. A transformer fire raging at the North Hyde substation. But fires alone don't usually shut down one of the busiest airports on the planet. Why this time had a single local incident spiraled so completely out of control? The answer lies in something hidden, quieter, and far more surprising. It involves a flaw buried deep in how our digital systems see the world. Small approximations, subtle shortcuts, and numbers that don't quite line up. In the story of Heathrow's shutdown, we discover how tiny computational cracks, unnoticed and misunderstood, can suddenly widen into massive real-world failures. Understanding why that happens, and how it happened at Heathrow, is crucial, because until we see these invisible cracks clearly, we won't be prepared when they appear again. A transformer works by converting electricity from one voltage level to another. As it does, it inevitably generates heat. Typically, a digital monitoring system continuously checks temperature sensors and cooling rates, ensuring things never reach a critical tipping point. Yet, these digital temperature calculations depend on simplified mathematical models, numbers rounded off, approximations of heat transfer, and interpolated lookup tables. Under ordinary conditions, this slight approximation is inconsequential. But when a transformer starts to heat more rapidly due to unusual load or environmental conditions, these small errors become critical. At Heathrow's North Hyde substation, as the transformer heated up on March 21st, the digital sensors monitoring it likely missed the crucial moment when internal temperatures moved from merely hot to dangerously unstable. An underestimated temperature, off by just fractions of a degree due to digital rounding or interpolation, meant cooling or load reduction measures never activated in time. By the moment the error became obvious, smoke billowing from the transformer, the physical system had already surpassed a point of no return. The result was an 18-hour shutdown, hundreds of thousands stranded and billions lost. But why did a fire at one substation cripple an entire airport's power supply? The answer lies in the hidden, fragile synchrony that holds modern power grids together. Electric grids rely on precise synchronization, a stable frequency heartbeat, 50 Hz in the UK, that keeps equipment harmonized. Digital sensors constantly measure frequency and phase angles to ensure every piece of equipment, from lighting systems to runway navigation aids, operates seamlessly. Yet, frequency measurement in digital systems is inherently approximate. Digital sensors sample voltage waveforms, digitally approximating frequency and phase. Tiny inaccuracies, mere microseconds or fractions of a hertz, quietly accumulate. During the Heathrow outage, as the grid rapidly shifted loads to reroute power, these subtle digital inaccuracies made it harder to accurately balance frequency across the network. The grid began drifting, and generators, detecting small yet persistent errors, began disconnecting protectively, further deepening the blackout. These tiny digital errors weren't the initial cause of the fire, but they amplified its consequences dramatically. Had these measurement systems been more precise, or at least better designed to anticipate approximation errors, grid operators might have more effectively isolated damage and stabilized frequency, greatly reducing disruption at Heathrow. As Heathrow scrambled to respond, operators relied heavily on SCADA, or supervisory control and data acquisition systems, digital maps showing real-time power flows and equipment status. But here again, digital approximations entered quietly, undermining crisis response. SCADA systems simplify reality. They digitally approximate the grid, sampling data from thousands of sensors, averaging, interpolating, and compressing information into a manageable format. Normally, this streamlined digital representation works. But during the rapidly evolving situation at Heathrow, these digital simplifications led to a distorted picture of reality. Operators saw inaccurate or outdated readings, digital hallucinations, caused by slight delays, approximations or interpolations, leading them to underestimate the urgency or misjudge the necessary response. This gap between digital perception and physical reality deepened the crisis. Decisions based on faulty or delayed digital models worsened the outage, prolonging chaos at Heathrow. What initially might have been a localized failure spiraled into a full-blown multi-hour disaster. The Heathrow incident wasn't just about one unlucky transformer. It was a vivid illustration of how tiny computational inaccuracies, embedded invisibly into digital systems, can escalate dramatically during real-world crises. If we want robust, reliable power grids in an increasingly digital era, we must acknowledge and actively manage the hidden risks posed by computational approximations. Engineers and policymakers should not only invest in physical infrastructure resilience but also improve how digital systems approximate reality. More accurate sensor designs, higher fidelity computational models, error-detecting safeguards, and better integration of digital and physical systems are urgently needed. Heathrow's shutdown provides a clear warning ignoring the invisible cracks in our digital foundations, risks magnifying small faults into disastrous failures. It's time we look closely, not just at wires and transformers, but at the subtle digital errors lurking quietly within the systems we trust to keep our modern world running.